In this lecture, we're going to look at orbital mechanics and then revision. The textbook reference for this lecture is sections 13.6 and 13.7. First of all, a quick recap of the most important ideas from the last lecture. In the last lecture, we finished looking at rotational motion. So we saw that torque is a turning force and it's given by torque is equal to R cross F. We saw Newton's second law for rotation can be written as the sum of the torques, which is the net torque, is equal to I, which is the moment of inertia, times alpha, which is the angular acceleration. We saw that the work done by a torque can be calculated using work done is equal to the integral of torque times d theta. We saw that rotational kinetic energy is given by K is equal to half I omega squared, and that angular momentum is conserved in the absence of a net torque, and it's given by L is equal to I omega. So we can also write torque is equal to dl dt, just as we can write for the translational case that the force is equal to dp dt. In the last lecture, we saw Newton's law of universal gravitation, which tells us that the gravitational force between two particles with mass m1 and m2 separated by a distance r is given by F is equal to g m1 m2 on r squared, where g is the universal gravitation constant. We saw that for an object placed on a rotating body, such as a planet, then the normal force, which is analogous to what the scales measure, is given by minus m omega squared r plus g mm on r squared, where the little m stands for the mass of the object and the capital M stands for the mass of the planet. The capital R here is the radius of the planet. We saw that gravitational potential energy is given by U is equal to minus g mm on R, and here the potential energy is taken to be zero, an infinite distance away. And we then showed that the escape speed for an object is given by V is equal to the square root of 2gm on R. So this is the speed that an object needs to leave a planet with in order to get an infinite distance away. So we're going to be considering orbital mechanics, that is mechanics about things in orbits. So let's start by considering a satellite in a circular orbit. Now, from the last section, we know that the gravitational potential energy of a satellite with a mass given by little m orbiting a planet with a mass capital M at a distance r from its center of mass, which is shown in this diagram here, is given by U is equal to minus g mm on r. Now we can also calculate the kinetic energy of this satellite. So we know that the kinetic energy is given by a half mv squared. Now if we consider the forces acting upon this satellite, which is undergoing circular motion, the only force acting upon it is the gravitational force. So we can say that the net force, which is the centripetal force given by mv squared on r, must be equal to the gravitational force, which is g mm over r squared. So rearranging this, we can cancel out this r with one of these r's, and we can then multiply both sides by a half, and we get a half mv squared is equal to a half g mm on r. So this here is the kinetic energy. So we can see that the kinetic energy is given by g mm over 2r. Now we can calculate the total mechanical energy, which is the sum of the potential energy plus the kinetic energy, by summing together U, which was minus g mm on r, with g mm on 2r, and you can see that's going to leave minus g mm on 2r. So this tells us the total mechanical energy of a satellite in a circular orbit. Now to practice using these equations, try homework set 3, question 11 for 1121 and question 15 for 1131. Okay, so here's a question. What happens? A satellite is in orbit. It turns on the thruster, providing a force in the direction it's moving. So we've got some planet here with some satellite going around it. The satellite's moving in this direction. It turns on a thruster, which gives it a force also in this same direction. So as a result, the satellite moves to a new orbit. and we're asked what happens to the speed of the satellite. Does it increase, decrease, or remain the same? Well, in this case, when the satellite turns on its thruster, the thruster is doing work on the satellite, and the work is given by the force times the displacement, and these are in the same direction. So it's doing positive work. So this is some positive number. And we know that when we do work on something, then we change its total mechanical energy. So this is equal to the change in the mechanical energy. So we can write, well, delta E is equal to the final mechanical energy minus the initial mechanical energy. And we've just seen that mechanical energy on the previous slide, we saw that E was equal to minus GMM onto R. So we can write, well, this is minus GMM onto RF, and then minus, so plus GMM onto RI, where RF is the final radius and RI is the initial radius. And this is equal to some positive number. So if this is positive, then it means that this term here must be larger than this other term here. So we can write GMM over 2RI is greater than GMM over 2RF. Now almost everything here cancels out. That occurs on both sides. This occurs on both sides, which tells us that 1 over RI is greater than 1 over RF, which in turn tells us that Ri must be less than Rf. So physically, this means that the final radius is greater than the initial radius. So it moves up to an orbit something like this. So here we've got Ri, and here we've got Rf. But this is us what happens to the speed. So to do that, we can consider the kinetic energy, because the kinetic energy is related to the speed. And we know that the kinetic energy is given by GMM divided by 2R. So if we're moving to a larger R, so as R goes up, then the kinetic energy decreases. And since the kinetic energy is also equal to a half mv squared, this tells us that if the kinetic energy is decreasing, the speed must also be decreasing. So it's possibly a surprising result, but when the satellite turns on its thruster, its speed does eventually decrease once it's stabilized into a new orbit. Okay, so here's an example problem for us. A playful astronaut releases a bowling ball with a mass of 7.20 kilograms into a circular orbit around the Earth at an altitude of 350 kilometers. So let's draw a little diagram. Here's the Earth, here's the satellite's orbit. This is definitely not to scale. This distance here is h is equal to 350 kilometers, and some other useful data which we can get off the formula sheet is that, the data sheet is that the radius of the Earth is equal to 6.371 times 10 to the 6 meters. So this radius should be much greater than this height here. And the mass of the Earth is equal to 5.972 times 10 to the 24 kilograms. So then in the first part of this question, we're asked, what is the mechanical energy E of the ball in its orbit? So this part is not too hard, though it is a little bit tedious. So we've got that the total mechanical energy is given by minus GMM over 2R. And R here is the distance between the center of the Earth and the satellite. So R is going to be equal to H plus capital R, the radius of the Earth. So this is equal to minus GMM over 2 times the radius of the Earth plus H. So now what we can do is just substitute in numbers and evaluate. So this is minus 6.673 times 10 to the minus 11 times little m, which is the mass of the bowling ball, which is 7.2, times big M, which in this case is the mass of the Earth, because that's the other object. So we've got 5.972 times 10 to the 24 divided by 2 times now the radius of the Earth, which is 6.371 times 10 to the 6, plus the height, which is 350 times 1,000 meters. So solving this on the calculator, we get minus 2.13 times 10 to the 8 joules. So in part 2 of the question, we're asked what is the mechanical energy E0 of the ball on the launch pad at the Kennedy Space Center before launch. So in this case, we can't use this equation here because this is the orbital mechanical energy, which describes an object in orbit, and while it's sitting on the launch pad, this object is not in orbit. It's in contact with the Earth, so there's normal forces and other things involved. So we know that E0 is equal to U0 plus K0. Now, it will have a small amount of kinetic energy because of the Earth's rotation, but this is so small that we can neglect it, because when you think about it, omega for the Earth is equal to 2 pi radians per day, and so the kinetic energy is going to be tiny. So we can ignore this because it's approximately equal to 0. So we just need to calculate the potential energy on the launch pad. So that is given by minus GMM on R, and the R in this case is the Earth's radius, and this is the mass of the Earth. So now we can substitute into here. So this is minus 6.673 times 10 to the minus 11 times the 7.2 times the mass of the Earth, which is 5.972 times 10 to the 24, divided by the radius of the Earth, which is 6.371 times 10 to the 6 meters. So solving that, we end up with minus 4.50 times 10 to the 8 joules. So we've answered the first part, and it says from there to orbit, what is the change, delta E, in the ball's mechanical energy? So delta E is equal to the final E minus the initial E. And we've calculated the final E in part 1. So this is equal to minus 2.13 times 10 to the 8. And then we calculated the initial E in part 2. So that's minus 4.50 times 10 to the 8. So solving this, we end up with delta E is equal to 2.37 times 10 to the 8 joules. And that's how we solve that problem. So this brings us to Kepler's laws. So Kepler's first law tells us that all planets move in elliptical orbits like this one with the sun at one focus. So an ellipse has 2 focuses, and the sun which it's orbiting around needs to be at one of these. So Kepler's second law tells us that a line that connects a planet to the sun sweeps out equal areas in the plane of the planet's orbit in equal time intervals. That is, the rate dA dt at which it sweeps out an area is constant. Okay, so let's see what this actually means by having a look at a simulation, and then we'll go ahead and actually prove it. So this is a nice simulation showing Kepler's second law. So we'll start sweeping, and it's showing the areas which are traced out in equal times. So you can see here we have a wide but shorter triangle, and over here there's a much longer but less wide triangle. So you can see how the satellite is moving slower when it's further from the sun, and then when it gets round to being closer to the sun, it goes very quickly. So let's prove this. Let's consider this triangle which the satellite sweeps out as it moves through the angle d theta. Well, we know the formula for the area of a triangle is just half the base times the height. So the area of this small triangle is given by a half. Now this length here is the radius, and then the length of our triangle is the arc length, which is r d theta. So we've got a half r squared d theta. Now, what Kepler's second law is telling us about is the rate of change of this area. So to get that, we're going to have to divide by dt. So we've got dA dt is equal to, now the radius is changing very, very slowly. So we can choose d theta to be small enough that the radius is constant. So then we've got a half r squared d theta dt, and we know what d theta dt is. It's omega, the angular velocity. So this is a half r squared omega. Now, r squared omega should vaguely remind you of moments of inertia. We've got that the total angular momentum is given by I omega, and the angular momentum is conserved. So if we assume angular momentum is conserved, then I omega is equal to a constant, and we've just got a planet, a point mass moving here. So I is given by mr squared omega. So we can say, well, rearranging this, we've got this is equal to L, our angular momentum. We can replace r squared omega with L on m. So dA dt is equal to a half L on m. Now the mass of the planet is definitely not changing, and as long as we assume that the angular momentum is conserved and isn't changing either, then we can see that dA dt is equal to a constant. So we've now proved Kepler's second law. So this brings us to Kepler's third law, which tells us that the square of the period of any planet is proportional to the cube of the semi-major axis of its orbit. So we've got this equation here. This one's not too hard to show, because when we consider the satellite orbiting around the planet, we know that it's undergoing circular motion. So the resultant force acting on the planet is just the centripetal force, which is given by mv squared on r. We also know what force is causing this resultant force. The only force between the satellite and the planet is the gravitational force. So this is equal to gmm over r squared. So we can cancel out one of these r's and the little m, which is the mass of the satellite. So we've still got the mass of the planet there. And so now we've got v squared is equal to gm on r. Now we know for the planet that the velocity is given by the distance divided by the time, which is 2 pi r over the period, which is t, and this is a velocity squared. So this is the velocity in here, and we're squaring it. So looking at this part of the formula, we can write, well, gm on r is equal to 4 pi squared r squared on t squared, which we can rearrange to say, well, t squared is equal to 4 pi squared, and then we've got an r squared here times an r here, so that's r cubed, divided by gm. And that is the formula which is written just here. So the square of the period is proportional to the cube of the radius of the orbit. So to practice using this, homework set 3 for 1121, try question 12, or 16 if you're in higher physics. Okay, so a question. Satellite 1 is in a certain circular orbit around the planet, while satellite 2 is in a larger circular orbit. So we can say from that that the radius of orbit 2 is greater than the radius of orbit 1. And we're asked which satellite has, in part A, the longer period. So to answer this, we're going to need to use Kepler's third law, which tells us that the period squared is proportional to the radius cubed. So if we have a bigger radius, we have a bigger period. So this tells us that satellite 2 has the largest or longest period. Now in part B, it's asking us about the speed. So possibly you remember the speed question that we did before, and we approached this one in a similar way. So to think about the speed, we know that K, the kinetic energy, is equal to a half mv squared, and it's also equal to gmm over r. So this So this tells us that v squared is proportional to 1 over r, or that if we have a smaller radius, we have a higher speed. So this tells us that satellite 1 will have the higher speed. So today we're going to look at some of the big ideas that were covered in mechanics. So we saw that there's two main approaches that we can use when answering questions. We can consider the energy, or we consider the forces and the momentum changes. So imagine that we had a question related to this figure where we've got two masses with a pulley and an inclined plane. Possibly there's some friction on this slope here. If you were given a problem to solve about this situation, which of these approaches would you prefer? Okay, so there's no correct answer to this one. Each of these approaches has some advantages and some disadvantages. With the forces, you do need to consider both the components parallel to and perpendicular to the slope, though admittedly you're probably going to have to do that anyway to work out the size of the frictional force. With energy, you need to remember to account for the work done by friction. So when friction is acting, energy is not conserved, energy is lost as work done against friction. But as long as you do everything correctly, both these approaches will give you the same correct answer at the end. Okay, so a question: when is energy conserved? And you need to select all the cases for which energy is conserved. So read over these and think about which ones are correct, and then we'll discuss them. You may want to pause the video. Okay, so energy is conserved when two carts collide elastically. An elastic collision is one in which no kinetic energy is lost, so therefore energy is conserved. Okay, when a cannonball is launched from a cannon and air resistance is negligible, then after it's been launched, the only force acting upon it is the gravitational force. The gravitational force is a conservative force, and so energy is conserved in this case. Now, when a bullet collides with a block and it becomes embedded in the block, this is an example of a perfectly inelastic collision. During perfectly inelastic collisions, kinetic energy is lost and it is not converted to potential energy. So in this case, mechanical energy is not conserved. A block slides up an inclined plane, friction is not negligible. Okay, well, friction is a non-conservative force, so in this case, mechanical energy is lost. So now we're asked, when is momentum conserved? And again, select all the cases for which momentum is conserved. So have a read through these, think about which ones will have momentum conserved, pause it while you think, and then play the video. Okay, so two carts collide elastically. This is a collision. During collision, the external forces are negligible, so momentum is conserved in this case. A cannonball launched from a cannon. In this case, once it's been launched, gravity is acting upon it, which is changing its momentum, so momentum is not conserved. A bullet collides with a block and becomes embedded in the block. This is a collision where the external forces are negligible, so momentum is conserved in this case. A block slides up an inclined plane, friction is not negligible. So in this case, we have an external force, the friction, and the weight force acting upon the block. So in this case, the momentum is not conserved. So then we had to look at the demonstration where a sudden force was applied to a plate supporting an egg, and the egg dropped vertically down into the cup, and we discussed the explanation of this. So essentially what is happening is that the horizontal momentum of the egg isn't changing, as forces are not acting upon it for any significant period of time, and so it doesn't have any horizontal momentum. So when the cup disappears from underneath it, it is acted upon by an unbalanced force. There's no normal force now balancing the weight force, and so it drops down into the cup below it. Okay, so types of energy. So we've seen that there's different types of energy, potential and kinetic energy, which can be translational, that's movement through space, or rotational, where it's being pivoted about some pivot point. So these are the two types of mechanical energy. So work is one way to transfer energy from one body to another and also convert between the two types of energy. So then we were asked which of the statements below is true. So read over the statements and pause the video and then replay it once you've had a think about each of these. So in fact, all of these statements are true. Energy is always conserved if we consider a closed system. If we consider a system which is big enough, then there is no way for energy to get into or out of the system. So for example, the energy of the universe is constant. The energy of an object is conserved whenever non-conservative forces do no work. Again, this is true. So for example, with a pendulum, if there is no air resistance, then the energy is continually converted between potential energy and kinetic energy, but it is conserved. And the change in kinetic energy is always equal to the net work done on the object. This is also always true. So we then saw a demonstration where we dropped a little ball on top of a big ball, and we saw that the little ball bounced a whole lot higher than the big ball. So the little ball ended up higher than the drop height and the big ball ended up lower. So one way to explain this is to consider the energy, and in this case the big ball was transferring energy to the small ball. So just after they left the ground, the small ball had more kinetic energy than it had initially, and this allowed it to get to a higher height. Okay, so a technique that came up a lot in this course was breaking an object into little components and then summing up the contribution of each of the components to work out the total force or the total energy. So here we're asked to list the types of problems that can be solved with the technique of breaking objects up into small components and then adding contributions of each of these components by integrating. So we always use that technique when we've got a continuous body rather than point particles that we're dealing with. And some of the things that we can find with this technique are total force, we can find the center of mass, we can find the potential energy, the gravitational potential energy, or we can find the moment of inertia. There may be others. If you can think of others, that's great. And then how do you solve each of these problems for a uniform ring? Okay, so let's imagine that we had a uniform ring here. Now, if we needed to consider the total force on an object a bit of a distance from a ring, what we'd need to do is break it up into little components. And here it actually helps to exploit the symmetry as much as possible. So we can see this component here is going to cause a force towards it, and this component up here is going to feel a force towards it. And this, if this is all drawn symmetrically, then you can see the vertical components are going to cancel each other out and the horizontal components are going to add. So what you do is you'd work out the size of the force from this component, which if it's a gravitational force would be given by F is equal to G times dm, where dm is the mass of this component, times m, this mass here, over r squared, where r squared is the distance between these two. Well, it's the square of the distance between those two. And so then, well, we call that df because that's the part of the force just due to this little component. So then we'd just work out the horizontal component, so df x, and if we had this was theta in here, this would be equal to g dm m over r squared times cos theta. And so then what we'd want to do would be to integrate over the whole ring. When we integrate over the whole ring, we'd just end up summing up all the dm's, so we'd end up with the total mass of the ring. So that's how we consider the total force. The center of mass, again, we always exploit the symmetry. So with center of mass, we can consider two little components opposite to each other, and we'd see that the center of mass for those two was right in the middle, and whichever components we consider opposite each other is always going to be right in the middle. So the center of mass would be right in the middle of our ring. For potential energy, that's kind of similar to force, but we don't need to worry about the vectors because it's not a vector. So because U is equal to minus G m on r, we again break it up into little components. So du, due to just one of these components here, is equal to minus G times m, where this is m, times dm on r, and then we'll just want to integrate these, and we end up with u is equal to minus G m times the mass of the ring on r. So for the moment of inertia, or the rotational inertia, it really depends upon the point about which we choose to pivot it. So in the lab, you worked out the moment of inertia of a disk about a point in the center, and to do that you used r squared dm, and you came up with an expression for dm, which was the mass in this case for the moment of inertia. You're splitting it up into little rings, like this little red ring here. You choose a little red ring with a thickness dr at radius r. You work out the mass of that ring and substitute that in there, and then choose appropriate limits on your integral. So have a look at your lab manual to remember how to do that one. Okay, so we saw Newton's law so many times. Newton's law is absolutely everywhere. So Newton's second law tells us that the net force is equal to the sum of all the forces acting upon the body, and that is equal to the mass of the body times its acceleration. So we could rearrange this to get our impulse equation to show how these are related. Let's write this as m dv dt. As long as we assume the mass is not changing, then we've got mv dt, and so this is equal to dp dt. So we can see that, well, f net is equal to dp dt, so f net dt is equal to dp, and then we can integrate these, and the integral of dp is the change in p. This is P initial, this is P final, so it's P final minus P initial, and that's equal to the integral of the net force with time. So that gives us our impulse equation, which is really just another way of writing Newton's second law. Now we saw Newton's second law also applies in the rotational case. So in this case, the forces are the turning forces, the torques, and the sum of all the torques gives the net torque, which is just the moment of inertia times the angular acceleration. Okay, so in this demonstration we had two tubes. Now the tubes actually had masses inside them. So one of them had masses a bit like this, and the other one had masses a bit like this, the same masses. And then we got two students to waggle them backwards and forwards and saw how exhausted they were after a certain amount of time. And it turned out that the student with this tube was much more exhausted than the student with this tube. So this was a nice example of moments of inertia, and again of Newton's second law, that the net torque is equal to the moment of inertia times alpha. Because this one here has a much higher moment of inertia, as the masses are much further from the point about which these tubes were being waggled, and so you had to apply a lot more net torque to this one to cause the same angular acceleration. Now, we've also been considering how we can interpret graphs. So whenever there's an integral, we can find the integral by working out the area under the graph. And if there's a derivative, then we can find the derivative by taking the gradient of the graph. So here's an example of a fairly challenging question that we could be asked about a graph. And there's always a few different ways that we can approach these questions. So the first question, what is the change in momentum of a 2 kilogram object that over the 7-second interval shown in the graph? So what we want to know is what's delta P. And one way we can do this is to use impulse, which tells us that it's equal to F dt, which is useful because if we had a force versus time graph, then we could just work out the area under this graph. Unfortunately, we don't just have a force time graph in this case, but what we can do is use Newton's second law to write the force as the mass times the acceleration. So this is the integral of the mass times the acceleration dt, which we can write as m times a dt, and we do have an acceleration versus time graph. So to work out the change in momentum, we can just do the mass, which we're given as 2 kilograms, times the area underneath this graph. So let's work out the area underneath it. Let's split it into a few different areas because we could consider this obviously as one triangle here, but for later it'll actually be easier if we split it up a bit this way. Okay, so if we consider this triangle here, it's got a height of 3 and a length of 3, so 3 times 3 is 9, and we just take half of that as the area, so that's 4.5. So next triangle is this one. This one here is going through 4.6. So this length here is 0.6 and the height is 3. So we've got 0.6 times 3 divided by 2, which gives us 0.9. Here we've got this triangle here, and this is below it. So this will be negative. And so here we've got the length is 0.4, the height is 2. So that is 0.4 as the area there. And then we've got this triangle here with a length of 2 and a height of 2. So this has got an area 2. So if we want to substitute into this to work out the change in momentum, then the mass is 2 kilograms, and we times it by these areas, which is 4.5 plus 0.9 minus 0.4 minus 2. And solving that, we end up with 6 kilograms meters per second, and let's put that as 6.0 because we'll assume that we can read everything to one decimal place. Okay, and then the second part says what would the velocity versus time look like, and we can assume that it starts from rest. Okay, so we'll want to have a velocity versus time graph like this. Here's the time, here's the velocity. Now the velocity is the area under an acceleration versus time graph. So let's sketch these times down. So 1, 2, 3, 4, 5, 6, 7. Sorry, it's not perfectly drawn. Now for the first second, it is not accelerating. So if it starts from rest, it's going to remain at rest and will have a nice horizontal line there. Between 1 and 4 seconds, it's accelerating, and the acceleration is at an increasing rate. So we can see from the area under the graph, which gives us the velocity, that at 4 seconds, its velocity should be, this is 4.5 meters per second, and that's at an increasing rate. So this is actually a parabola where it's curving up and going through there. Now between 4 and 4.6 seconds, so let's put 4.6 here, we've still got a positive acceleration, but it's at a decreasing rate. At 4.6 seconds, the acceleration is 0. So we can see that the velocity is going to increase by another 0.9. So 4.5 plus 0.9 gets us up to 5.4. So, sorry, this is really not to scale. So that's up to 5.4 there. And so this is going to be another parabola, but it's bending in the opposite direction. And then between 4.6 and 5 seconds, its velocity decreases by 0.4. So we're going down to 5 meters per second. So that's like this. And it's at an increasing rate, but in the negative direction. So we have a parabola which is bending round like this. And then between 5 and 7 seconds, the magnitude of the acceleration is decreasing, but it is in the negative direction. So even though the velocity is still positive, that's slowing. And so in this time, it slows down 2 meters per second. So we're going down to 3 meters per second here. So this will be another parabola which looks like this. So that's a rough sketch of what the velocity versus time graph would look like. So next we had a look at this possibly slightly surprising demo where we had a cup and a ball on a length of rod here. Now the cup is actually screwed to the length of rod, whereas the ball is free to move, and we notched this supporting piece of metal, which is actually a ruler, out of the way, and we saw that the ball actually landed in the cup. And we discussed how that could work because at the moment they're not aligned horizontally, but of course the cup undergoes circular motion as it comes down, and the ball just experiences the gravitational force, so falls down like this. And so then we're asked, how could you calculate how fast the pole is moving just at the end of its motion? Okay, so if we make the assumption that the pole has uniform density, then we can model all its mass as being at the center of mass here, which is halfway along the pole. So let's call the length of the pole here L, and we'll call the height of the center of mass here H, and we'll call this angle in here theta. And the only forces acting once it's been released are the gravitational force. So we can say, well, energy is conserved. And so we've got U initial plus K initial is equal to U final plus K final. The initial kinetic energy is 0 for the end of the pole because it's at rest. The final potential energy is 0 because it's coming down to this horizontal position with height equals to 0. So we've got mgh is equal to, now in this case, this pole is pivoting about this point here. So rather than having translational kinetic energy, it's got rotational kinetic energy. So that's equal to a half I omega squared. And for a rod pivoted about one end, we've shown that I is equal to a third ml squared. So we can substitute this in, and we've got a half times a third ml squared times omega squared, and that's equal to mgh. And h here is the height of the center of mass. So this is right in the middle of the rod. So this is L on 2. So hopefully you can see from here that h is equal to L over 2 sine theta. So we can cancel out the m's, and then we'll put g times L over 2 sine theta is equal to a half times a third L squared omega squared. So the halves will cancel out, and we can now use V is equal to omega r, and in this case the radius is L because we're considering a point on the end of the rod here, so this is equal to L. So we can write GL sine theta is equal to L squared on 3 times omega squared, which is V squared over L squared. And so these L squareds cancel out, and we end up with V squared is equal to 3GL sine theta, and so the velocity is equal to the square root of 3GL sine theta. So we could use this to work out the velocity of the end of the rod just before it hit the ground. Now, if for a comparison we want to work out how fast this ball is going, the ball is not connected to the rod. So we can use V squared equals U squared plus 2AS. Now it starts from rest, and S is this height here. Let's draw it in green. It's this height. This is length L. So this height is given by L sine theta. So we can say, well, V squared is equal to 2. Now the acceleration is due to gravity, and the displacement is L sine theta. So you can see the velocity of the ball is given by the square root of 2g L sine theta. So the cup is actually moving slightly faster than the ball at the bottom here. Okay, so another thing that we looked at was this apparatus here, and we thought about how we could calculate the acceleration as the hanging mass dropped. So essentially what we have is an almost massless rod with a mass here, let's give it lowercase m, and a mass here, same mass, and we'll place them at a distance capital R from the center of the rod. And then this rod is connected around a kind of fattish, again we'll assume it's massless beam with a radius little r, and then we've got a string wound around here with some hanging mass which we'll call capital M here. Now if we assume that these two rods are massless, then the moment of inertia of this system, it's just 2-point masses, and we'll call them both a distance r from the pivot. So the moment of inertia of the system is given by 2mr squared. And so we can use Newton's law to write down, Newton's second law, to write down equations for the hanging mass and also for the 2-point masses here. So for that hanging mass, we've got a tension app. So we've got MA is equal to mg, which is pulling it down. So let's draw a little free body diagram. We've got mg pulling it down, and we've got the tension force pulling it up. So this is minus tension. Now the tension here is acting as a turning force. So the tension is up against here, and this has got radius little r here. So the torque which is causing these two masses here to turn is caused by the tension force. So we can use Newton's second law for rotation to write I alpha, which is equal to I is 2mr squared. Okay, and then we've got the angular acceleration, and we can write the angular acceleration as alpha is equal to the acceleration over, we're looking at the acceleration here, the tangential acceleration at this point, so this is over little r. So this is times a over little r. And this, according to Newton's second law, is equal to the net torque, and the only force which is acting to apply the torque is the tension force acting here. So that's equal to r, it's lowercase r here because it's acting at this smaller radius, times the tension force. Okay, so let's divide both sides of this part by r. So we've got that the tension force is equal to 2mr squared a over r squared, and we can now substitute that back into this equation here. So here we've got mg minus 2, this is lowercase m, these masses here, times r squared a over r squared. So we want to rearrange this to get the acceleration, so we'll move this over to the left hand side, and we've got the mass times, well, plus 2mr squared on r squared times a is equal to mg, and so we've got the acceleration is equal to mg over m plus 2mr squared on r squared. And this gives us an expression for the acceleration of this hanging mass as it falls. So in this problem, a spaceship of mass 4.5 times 10 to the 3 kilograms is in a circular Earth orbit of radius 8 times 10 to the 6 meters with a period of 118.6 minutes or 7.119 times 10 to the 3 seconds when the thruster is fired in the forward direction to decrease the speed to 96% of the original speed. And part A asks what is the mechanical energy of the satellite in its new orbit, and part B says what is the period t of the resulting elliptical orbit. So in this problem we've got a spaceship with a mass of 4.50 times 10 to the 3 kilograms. It has got initially a circular orbit with a radius of 8 times 10 to the 6 meters per second, and its initial period is equal to 118.6 minutes, which is equal to 7.119 0.519 times 10 to the 3 seconds. So it's thrust as fire, and that decreases the speed to 96% of the original. So if we've got the final speed is equal to 0.960 times the initial speed. And in part A, we're asked to find the mechanical energy of the orbit. So the easy way to do that would be to just substitute into the formula minus gmm over 2a. But in this case, we don't know what a is, so we can't just solve it this way. So instead, we're going to have to look at E is equal to U plus K and calculate U and K separately. Okay, so the potential energy, U, now just after the thrusters fire, it's still going to be at radius r. So when a rocket fires its thrusters, it doesn't suddenly disappear from the spot it's at and reappear somewhere else. It stays at that radius for a short amount of time, but firing its thrusters will make the radius of the orbit eventually change. So we can say this is equal to minus g mm on r, and this r is the initial r that it was at. So this is equal to 6.673 times 10 to the minus 11. Now times the mass of the Earth, which is 5.972 times 10 to the 24, times the mass of the satellite, which is 4.50 times 10 to the 3, divided by r, which is 8.00 times 10 to the 6. Sorry, that shouldn't be meters per second. I've miswritten the units for there. That should be meters. And so solving this, we get U is equal to minus 2.42 times 10 to the 11 joules. Now the other thing we're going to have to find is K. So it does slow down straight away. So we're going to need to find the final kinetic energy, which is a half mv final squared. Okay, so to do this, we're going to need to calculate V final, and we know that it's 0.960 times V initial. Now, we can work out V initial because we have the period and the radius of the original orbit. So we can say, well, V initial is going to be the distance it travels, which is 1 radius, over the period, which is T0. So this is 2 pi times 8 times 10 to the 6 divided by 7.119 times 10 to the 3. And solving this, we get the initial speed as 7,061 meters per second. So the final speed is equal to 0.960 times 7061, and that is equal to 6,778 meters per second. Okay, so now we can substitute in here. So we've got a half times 4.50 times 10 to the 3 times the 6,778 squared. And solving this on the calculator, we end up with 1.034 times 10 to the 11 joules. Okay, so now we've got the potential energy and we've got the kinetic energy just after the thrusters have fired. So now we can calculate the total mechanic energy just by adding those together. So we've got minus 2.42, sorry, I left off a 2 here, 2.242 times 10 to the 11 plus 1.034 times 10 to the 11, and that gives us minus 1.208 times 10 to the 11. And since most of the things were given to 3 significant figures, we should give our answer to 3 significant figures. So this is minus 1.21 times 10 to the 11 joules is the total mechanical energy just after the thrusters have fired. So for part B, we're asked to find the period. To find the period, we're going to have to go back and use Kepler's third law, the law of periods, which tells us that T squared is equal to 4 pi squared over gm times a cubed. or r cubed for a circular orbit, a cubed for an elliptical one. So in order to do this, we're going to need to find a, but as we highlighted up here, we can use E, our total mechanical energy, now to find A, as A is now the only unknown in this equation. So our next step is to find A. So let's rearrange this equation in the purple box, and we can say, well, A is equal to minus G mm over 2E, which is equal to minus 6.673 times 10 to the minus 11 times 5.972 times 10 to the 24 times the 4.50 times 10 to the 3, all divided by 2 times, and this is minus 1.208 times 10 to the 11. So we enter all this into the calculator, and when we get that, we get A is equal to 7.423 times 10 to the 6 meters. Okay, so now we've got A, so now we can find T. T is equal to 4 pi squared over G, which is 6.673 times 10 to the minus 11, times M, the mass of the planet, which is 5.972 times 10 to the 24, times A cubed, which is 7.423 times 10 to the 6 cubed, and then we need to take the square root of this. So when we do all that on the calculator, we end up with 6,365 seconds, which is equal to 106 minutes. So that's how we solve that problem. So in this problem, a 20 kilogram satellite has a circular orbit with a period of 2.4 hours and a radius of 8 times 10 to the 6 meters around a planet of unknown mass. If the magnitude of the gravitational acceleration on the surface of the planet is 8 meters per second, what is the radius of the planet? So we need to try and find radius. So let's start by considering an object on the surface of the planet. So consider an object on surface. Then we know that the gravitational force is mg, where little m is the mass of the object, and we know that that's equal to g m on r squared, where capital M is the mass of the planet and capital R is the radius of the planet, and this is because the object is a distance r from the center of the planet. And so the mass of the object cancels out, and we can write this as r squared is equal to g m on little g. Now the problem here is that the mass of the planet is unknown. So we're going to have to come up with another expression to find the mass of the planet so that we can get this radius here. So to do that, let's consider the satellite in orbit. And for the satellite in orbit, we know that it obeys Kepler's laws, and in particular Kepler's third law, which tells us that the period squared is equal to 4 pi squared on gm times r cubed. And so we can rearrange this to get an expression for m. So we can see m is equal to 4 pi squared r cubed divided by t squared g. And we can now substitute this back up into this equation. So we've now got g on g times 4 pi squared r cubed divided by the period squared times g. So our universal gravitational constant cancels out from the top and the bottom, and now we can substitute in the values from the question. So we've got 4 pi squared times r cubed, which is 8.0 times 10 to the 6, so that's cubed, divided by little g, which was 8, times the period squared, and the period is 2.4 hours, so it's 2.4 hours, and then there's 60 minutes in an hour and 60 seconds in a minute, so that is squared. So we can then solve this on the calculator, and we end up with 5.8 times 10 to the 6 meters, and I've given this to two significant figures, as the values in the question are all given to two significant figures. So in this problem, we're told that one way to attack a satellite in Earth orbit is to launch a swarm of pellets in the same orbit as the satellite, but in opposite direction. Suppose a satellite in a circular orbit 500 kilometers above the Earth's surface collides with a pellet having a mass of 4 grams. Part A, what is the kinetic energy of the pellet in the reference frame of the satellite just before the collision? And part B, what is the ratio of the kinetic energy to the kinetic energy of a 4-gram bullet from a modern army rifle with a muzzle speed of 950 meters per second? Here's the Earth. We have a satellite here which is at a height of 500 kilometers above the Earth. Got radius of the Earth here, so again, not to scale. If we want to get the radius of the orbit, then it'll be the radius of the Earth plus the height, so that'll be 6,371 plus 500 kilometers. So in this question, we're told that one way to attack this satellite here is to launch a swarm of pellets which are traveling in the opposite direction. Now, to be in the same orbit, when they're moving in the opposite direction, they're going to have the same speed, because the speed is set by the height of the orbit. And we're told we can assume that the mass of the pellets is equal to 4 grams. And then in part A, we're asked what is K of bullet in frame of satellite. Okay, so to work out K, we'll need to go back to our equation that we learned ages ago. The kinetic energy is equal to a half mv squared, but this tells us that we're going to need to know, well, what's this V here of bullet in satellite's frame. So we're going to need to use what we're told in the question to work out the speed of the satellite, and then once we know the speed of the satellite, we know that the speed of the bullet is equal and opposite to that, so then we can get this relative velocity here. Okay, so we know that the kinetic energy for the satellite is equal to G times the mass of the satellite times the mass of the Earth over 2r, let's put little s there, and that this is equal to a half mass of the satellite times the speed of the satellite squared. So we can use this equation here to get the speed of the satellite. Now looking at this, we can see there's a couple of things which will cancel out. The mass of the satellite will cancel out, and these halves, the 2's on the bottom, will also cancel each other out. So we can rearrange this to get an expression for the speed of the satellite. So the speed of the satellite is equal to G times the mass of the Earth over r. And so this tells us that V is equal to square root of G times the mass of the Earth on r, where r was defined over here. Okay, now the speed in the satellite's reference frame, it is at rest and it has the bullet traveling towards it. The velocity of the bullet relative to the satellite is equal to the velocity of the bullet minus the velocity of the satellite. And in this case, the satellite is going this way with some velocity, and the bullet is going this way with some velocity, same velocity, but in opposite directions. So this expression, which we've just derived, defines both of these. This negative sign here will mean that these two end up adding together. And so we have that the velocity of the bullet relative to the satellite is equal to 2 times G times the mass of the Earth on r. Okay, so now we've got the relative speed, so that's what we needed to put in here. So K for the bullet in the satellite's reference frame is given by a half times the mass of the bullet times 2 root GME on r squared. And so this is equal to 2 mg times the mass of the Earth over r. And then we can substitute in, so we've got 2 times 4 grams, so that's 4 times 10 to the minus 3 times 6.673 times 10 to the minus 11 times the mass of the Earth, which we grab off the data sheet, 5.972 times 10 to the 24 over r, which is here. This is 6,371 plus 500, and then that's kilometers. So we times it by 1,000 to get it into meters. Solving this, we end up with 463,992, which we can write as 4.6 times 10 to the 5 joules, to two significant figures. Now, part B asks us to compare this kinetic energy of the orbital pellets to the kinetic energy of something coming out of a rifle with a muzzle velocity of 950 meters per second. So to get this kinetic energy, we just do a half mv squared, which is equal to a half times 4 times 10 to the minus 3 times 950 squared, which is equal to 1,805. So to get the ratio of K in space over K from rifle, we do 463,992 divided by 1,805, and that gives us 257 or 260 to two significant figures. So the moral of the story is here, you don't want to get hit by orbital debris traveling in the opposite direction to you in your orbit in space. It has a lot more energy than equivalent amount of matter coming out of a gun on Earth. So it would do a lot of damage.